All right, I'm Derek Driggs, and I'm going to talk about a way to develop faster stochastic gradient methods. And this is joint work with my supervisor, Dr. Carola Schoenlieb, and as well as Dr. Jingwei Liang and Dr. Clarice Poon, both in the Applied Math department here at Cambridge. So I'm interested in minimizing sums of functions, and in particular, objectives of this form. So we have a sum of smooth differentiable functions and also a non-smooth term, g. And I'm interested in this problem because it arises all the time in machine learning. So this, the sum of smooth functions you can think of as the L2 norm, and the non-smooth part could be the L1 norm or the nuclear norm. And we see that lasso, robust PCA, logistic regression, and actually a lot of methods talked about in earlier talks today, they all fall within this framework. So there are many applications for these types of problems. And solving this problem actually isn't too difficult. So because the f sub i's are all smooth, we can compute their gradients thanks to our friend on the wall here. And for the non-smooth term, it's a little trickier. But if we introduce this prox function, we develop this algorithm called proximal gradient descent, and we can solve these problems with relative ease. And now the problem arises when we have many, many functions. So n becomes large. And in this case, computing the gradient of f is very expensive. So what people do now is choose an index, an f sub j, where this index is chosen uniformly at random. And then we use the gradient of this single function to approximate the gradient of the entire function. And so here are three different examples of stochastic gradient descent methods that use different gradient estimates. And the two important ones for us are Saga and SVRG. And yes, so when we're measuring the performance of these optimization algorithms, we want to bound how far we are away from the solution we are at iteration k. And so proximal gradient descent achieves a 1 over k convergence rate. And we can also show that SVRG and Saga achieve a 1 over k convergence rate and expectation. And we would like to do better. So for proximal gradient descent, we can use Nesterov's momentum trick to accelerate its performance and achieve a 1 over k squared convergence rate. And this is actually a significant improvement. So this momentum method is like the fast Fourier transform of our field. And so it would be great to extend this to the stochastic case. And what goes wrong in the stochastic case is if we evaluate a bad gradient evaluation at some iteration and we apply momentum, then we carry this bad gradient evaluation for all future iterates. So these errors can compile and cause problems. And recent work, the algorithm Katyusha of Alan Zhu from last year showed that introducing a negative momentum term can balance out the effect of the problems that arise from doing statistical gradient estimates. And this algorithm can achieve the optimal 1 over k squared convergence rate as well. But this algorithm is very limited because it only works for SVRG because this negative gradient or this negative momentum term is tied to a full gradient that's computed in SVRG. So to extend this to other algorithms, we have to remove this dependence on the negative momentum term. And using similar analysis, we've shown that this is actually possible, and we don't need this negative momentum term to achieve the optimal convergence rate. And through this proof, we develop a framework for accelerating all sorts of stochastic gradient algorithms, including Saga. So this is just an example applying our procedure to a logistic regression problem. And naturally, our algorithm is the fastest one shown here. And it's just applying our framework to accelerate Saga rather than SVRG. All right, thanks for listening.